All right. So I just asked everyone here if they understood what the circuit did, and it was a resounding no. So we're going to go ahead and just reform it a little bit. So Vicky went ahead and said, the electrical engineer will give you the circuit and all that, in the industry. For my sake, that's kind of fake. I'm a very self-induced project designer, I guess. And the point of these workshops is to allow you to do some projects yourself. So in case you have a big circuit that you would like to go ahead and make into a PCB, you're going to have to be the electrical engineer and you're going to have to be the PCB designer. So in an industry setting, of course, you got to split the work amongst a lot of people. So if you want to go ahead and do PCB design in the industry, well, of course, you're going to have to, design PCB and not be doing all the electrical engineering work, right? The core of this circuit is literally these two ICs right here. This is the AMS1117. It's a fixed voltage regulator. So for those of you who went to the circuit construction workshop, that term should be pretty familiar, right? So it takes any voltage higher than it and lowers it down to a fixed value. In this case, for U1, this will lower it down to 5.0, and this will lower it down to 3.3. Daisy chaining, like Sam said, is not directly for electronics. It's usually using like networking and host computing, but in this case, we're going to use it for electronics because they're right next to each other. So it's the process of chaining different voltage regulators together. That's what we call it that. The rest of the circuit, you can kind of just ignore it, and we'll go through this in KiCAD step by step so you know how to build it. But when you're building circuits from scratch, you want to start from the main components. In this case, voltage regulation. Everything else comes later. Everything else is a feature. There are the filters, which is a feature to make you guys have better noise. You have a diode for reverse polarity protection. Again, this is kind of from the construction workshop. This prevents you from accidentally switching the battery backwards and causing the entire thing to explode, right? You have switches, so you can turn this thing on and off. You have headers, so that you can connect outer wires to it. You have LED circuits, so that you can see if the board is on or not, because that's kind of important. Like if you want to plug this into a power source, you want some kind of indication that this thing is on, right? And that's pretty much replicated all around the board. So in all, it's not a difficult circuit. I would even consider it to be like a hello world for PCB design. The only thing that makes it complicated is like everything else other than these two chips. As long as you can build these two things, boom, you've got yourself a voltage regulator. Everything else is what makes it from like a 10-cent board made in China to like a $5 board you can order from like, someplace else. So we're going to go ahead and start designing this board in KiCAD. KiCAD has a nice little UI. I actually think I like KiCAD better than Altium just because of its simplistic user interface. And usually user interface is very important when it comes to this sort of thing. Move the camera up here. Okay. So when you are designing PCBs, you are going to have two main files. One file is going to be your schematic, and one file is going to be your actual board. So the schematic is what you see up there, right? It's just all these circuit diagrams connected in place. The PCB board is where you can drag all the components into place and then actually make that 3D model you see there. And then from that 3D model, you can order it at like a fabrication company, like a JLC PCB or something similar. So we're going to go ahead and create a new project. So new project, and I'm going to save it in my KiCAD folder. I'm going to make a new folder, and I'm going to name this. I'm going to name this thing voltage regulator demo. All right, and I'm just going to open it. My file name. Voltage regulator demo. All right, pretty simplistic. Okay, when you go ahead and create this file, you're going to get presented with two subfiles on the top left bar. This is going to tell you what's actually inside your folder, so when you get to producing it in like a real board, it's going to have more stuff there. But for right now, you'll see two files. One has a PCB symbol and one has a schematic symbol. We're going to go ahead and open the schematic symbol. And we're going to copy the default global symbol library table. The default global symbol library table consists of all the different, very common SMD and THT components. KiCAD is beautiful for doing this because in Altium, you would have to go log online to Mouse or Electronics, find the part name of like a resistor, drag it into the library loader, and all that. You don't have to do it for KiCAD. If you want a specific part, of course, you're going to have to do something like that. But in this case, for our example, we're not going to find specific examples. So what I'm going to do here is I'm going to go ahead and show you how to place components. So again, as we've said, the voltage regulator PCB primarily consists of two IC chips, right? You have the first IC chip, which is the AMS117, that turns it from 9 volts to 5 volts. So you're going to go ahead and go to place, and then you would place a symbol, and it is currently loading, and it's currently not responding. Great. So you guys should go to place, and then place symbol, and then hopefully you'll get better luck than me. Great, it loaded. So once you've loaded, you can see that there are 17,000 items, and these are all different libraries that you can select things from. In this case, you have a lot of different things. You have amplifiers, you have IC chips, but we're going to go ahead and type in AMS1117. All right. Now, when you type in that, you'll see a lot of different variants. Now, when we introduced AMS117 in the circuit analysis workshop, we said that this variant was an SMD component that had fixed and adjustable values. You can see that there are different variants. You have 5.0, you have 3.3, you have the adjustable version. I'm going to go ahead and select 5.0 because that's the one we're using. And then I'm going to go ahead and press OK and drag it onto my schematic. And there we go. We have a 5.0 volt AMS117. All right. Now we're going to do the same thing. I'm going to go back to place and add symbol. And then I'm going to go ahead and do AMS1117. And then I am going to select 3.3 volts. All right. Now this circuit symbol here is pretty simple to understand. There are 3 terminals. So this terminal is for voltage in, this terminal is for voltage out, and this is for ground. There's literally 3 things you should plug in here. It's very simple. Voltage in is for your higher voltage. Voltage out is for 5 volts. 5 volts is always going to come out of this because it's a fixed voltage regulator. And ground is also going to connect to the ground, right? So this whole thing is a voltage regulator that turns higher voltage into 5 volts. A fixed voltage. So you're not going to be able to change the voltage here with resistors or anything like that. So let's go ahead and do that. I'm going to go ahead and place a ground. So I'm going to add power. And then under power, I'm just going to put ground. You can do ground or earth. I usually like the earth symbol better because it looks cleaner. So I'm going to go ahead and place one here. And then I'm also going to place another one next to the other one. Now, if you don't like having multiple ground symbols in your schematic, you can, of course, go ahead and connect them both to each other because they're all connected to ground anyways. But what I'm going to do is I'm going to go ahead and click from ground on the AMS117 onto the ground symbol, and we have made our connection for the ground pin on the AMS to ground. And that's literally it, right? Now, we're going to do our daisy chain next. Remember, we have to take our voltage from the 5 volts output and feed it into the input of the AMS117. So whatever voltage comes out of pin 2, which is 5 volts, will go into the voltage in of the regulator. So then it's what this, this symbol is going to take 5 volts and turn it into 3.3 volts. Okay, so now we have 2 IC chips in our schematic. We need to have a way of putting power into our circuit and a way of taking power out. So what I'm going to do is I'm going to go ahead and make a wire here. So to end the wire early without connecting to another junction, I just double click. And I'm going to put another wire out this area. So this will tell me that I can put 9 volts in and then take 3.3 volts out. Right? Kind of like our function generator in a sense. In addition, because I always also want to probe 5 volts from the circuit, I'm going to go ahead and put a wire in the middle. So in this case, what I've just done is I have given myself a way to put 9 volts into the circuit. I'm going to put the text there. You can press T to open up a text box and put text all over the place. I'm going to put my 5 volts here. And remember, this is just text, so it does nothing to the rest of the circuit. And then 3.3 volts. Now, in some circuits, you'll actually see the symbol 3v3 instead of 3.3 volts. This is because, some people got lazy, decided that decimals were too hard to read, so they just put a V in the middle to tell you that that's 3.3 volts. So once we put that text symbols there, we can clearly see what the function of the circuit is, right? 9 volts input, 5 volts output, and also 3.3 volts output. The next step is we need to put a terminal block so that we can actually wire something to the circuit. So let's go ahead and go to place, go to add symbol. Huh?
Except for just press A.
Press A?
Yeah.
Oh, yeah, you can press A. And then I believe the part is terminal block. Let me see, here it is. So when you press in terminal, you'll see that you have options here. We're going to use the screw terminal, which is the 0x102. These terminal blocks are already given to you within KiCAD's global library, which is why it's so amazing. And you have different terminal connectors. So if you want a 3 or a 4 or a 5, it'll correctly map it to the right location. So here we're going to go ahead and place 3 of these. And these terminal blocks are kind of like, these are your blue pieces with a screw on top from the last workshop. And you can see that each of these have 2 terminals. Now, you're going to want to form some sort of convention when going ahead and putting it into your circuit. I like to say that 1 is going to be my power and 2 is going to be my ground. If you flip that up or mess it up, it's going to be a little bit difficult to represent in the rest of the circuit. I'm going to go ahead and place this into my circuit. So this bottom one, I'm going to put in my 3.3 volts or near it. This middle one, I'm going to go ahead, hold it, and I'm going to press R to rotate it, and I'm going to position it above the 5 volts. Next, I'm going to take this one, I'm going to press X in order to flip it, and then place it next to my 9 volts. All right. Now I'm going to position my 1 pin close to where the power is, so close to where the 5 volts, 9 volts, or 3.3 volts is. And then I'm going to connect it and finish the circuit up. All right. So in this case, what I've done is I have connected a screw terminal block to my circuit. The 1 represents power, 2 represents ground. So I would need to put 2 connected to a ground. In this case, I can just copy and paste my ground into each of these connections. Okay, so now that we have this, if we built the circuit out, we can stick wires into the screw terminal, and if there were 2 wires here attached to a 9 volt battery, it would provide the circuit with 9 volts. And then the AMS 117 would turn this 9 volts into 5 volts. And then if we move along the circuit, the 5 volts would enter this module, and this module would turn 5 volts into 3.3 volts. These are known as our access points. So we can access 5 volts from the top terminal block, and we can access 3.3 volts through the right terminal block. Therefore, if we wanted to connect an Arduino to 5 volts and an NRF24L01, like an RF communication module, to 3.3 volts, we can. And it will be a physical connection. Are there any questions so far? Is everything clear? Cool. Okay, so next, let's talk about capacitors. So you will need capacitors in this sort of PCB design in order to filter the voltage out. When you're plugging like a 9 volt battery into the system, these batteries provide charge through chemical reaction. And these chemical reactions can sometimes be unstable. So you're going to get like noisy voltage coming into the AMS 117. Noisy voltage is bad because sometimes that going into an Arduino will confuse it a little bit. It'll give it like scrabbly data. We don't like scrabbly data. We want smooth and accurate data. Therefore, we need to filter out noisy voltage. We do this using capacitors. So we're going to go ahead and go to place symbol or just press A, and we are going to go ahead and type in capacitor. So when we type in capacitor, it's going to show us a bunch of stuff on the top, but we're going to scroll down and we're going to choose C. This is going to be a ceramic capacitor or an unpolarized capacitor. So we're going to double click this and we're going to place it in our circuit. Okay, now in our circuit, we are going to need 6 capacitors. We're going to need 2 capacitors to go before the regulator, 2 in the middle, and 2 at the end. The reason why we need two capacitors of different values is because we need to filter big signals out and then small signals out, right? Because if a noisy voltage passes through like a 10 microfarad capacitor, there may still be a chance that there are like slight murmurs in the voltage. And you know, like some sensitive circuits cannot take that. So that's why we use two capacitors. It's kind of like overkill, but it's a good kind of overkill. You want to be protected against, you know, stray voltage. So we're going to go ahead and duplicate this capacitor a bunch of times. And then it is time to do some positioning. So I don't know if you guys have you know, an OCD sense, but I do. And this is the part where it's either, you know, the best part of circuit design or the worst part of circuit design, because you get to position everything in place. All right. So we are going to place these capacitors here. Whoop. And if you need to move some components around, you can. Okay. So I'm going to connect one side of the capacitor to my voltage line, like so. And then the other side will go straight to, anyone know? Ground, right. So under normal circumstances, capacitors under DC voltage, they act like an open circuit. So usually voltage isn't able to travel through them. However, if there's any sort of like AC voltage, in which if you have like noisy voltage, that is considered AC because it's, you know, moving, it will go straight through the capacitor and into ground. That's why it acts as a good filter. So we want to remove all the noisy voltage, all the excess voltage, and put it into ground so that it doesn't disturb the rest of our circuit. So I'm going to go ahead and complete this wiring. Now the next step I'm going to do is I'm going to go ahead and change the value of these capacitors into what they actually are. Now every symbol comes with a designator and a value. The designator follows the part into the PCB. So when you're making your PCB, you might see your designator appear. In this case, we're going to go ahead and label the values first. I'll talk about the designators later. So I'm going to use a 10 microfarad capacitor as my big one. So when the voltage passes through this capacitor, it's going to smooth out a lot of it, but not, you know, all of it. And then it'll pass through the 0.1 microfarad, in which it'll remove the murmurs, right? And then smooth voltage will pass into the AMS 117. When it comes out of the AMS 117, it might get scrambled again. This IC chip is consistent of a lot of transistors, a lot of parts that have the ability to screw up your end voltage. And by screwing up, I mean making it look like an earthquake. So we want smooth DC voltage, which is why we pass it through two more capacitors. And these capacitors, I'm going to name it 10 microfarad and 0.1 microfarad. Same for the last one. Okay. Now, these capacitors are a feature, right? They're not, you know, at the core of our circuit. They're not really needed unless you want your circuit to work better. Remember, this is like the difference between a Chinese circuit and a really nice made circuit, you know, that you make yourself, like a custom one. So it's kind of like a protection measure. It protects you from getting your circuit destroyed too early. Now, the next step here is to go ahead and replace the designators with part numbers. So this is how each part is going to get its name, right? We don't want every part to have the same name, otherwise, you know, the PCB design software will get confused. So I'm going to go ahead and name these different numbers. So let's say that capacitor on the left is C1, and then C2, C3, C4, C5, C6, going down the line. And you will need to do this for every single part. So for example, the AMS 117s, you're going to name that U1, and the next one, you're going to name it U2. You can do it automatically, but I'm just showing you manual changes as of right now, just in case you want to name it something different. Okay. Because if you do it automatically, sometimes it does it out of order, and you want to keep, let's say, C1, C2 on the left, and C5, C6 on the right. I don't like to do it automatically unless I have like a really large schematic. Manual is always better. Same for auto routing. We'll talk about that later, but Altium has a feature called auto routing that sometimes screws that as well. Okay, So what you need to do next is take a look at your circuit and you're gonna say, does this fit what I need? When you make the circuit for something else, let's say you're making a circuit for an RC car, right? You're gonna need some way to connect a Arduino to its motor driver. You're gonna say, is this what I need? Can I put a battery into my circuit and have it come out as 5 volts and 200 amps? And in this case, actually yes, the circuit is pretty much done, right? But we want to add some more features, right? There are some features that are very necessary that will make the circuit even better. Features such as switches, LEDs, and I think those are the only 2 things left. So the reason for switches and why I want to put them in the schematic is because of something like, if we don't use this PCB for a long period of time and we still have this plugged in, it'll continuously drain the battery because these things require power to survive or power to do their thing. So in order for us not to lose out on our 9-volt battery and not have to unplug it, we're going to implement a switch. It's kind of like everything you see in kids' toys, right? You want to switch things off when it's done. The switch we're going to use is called an SPDT switch. An SPDT switch is known as a single pole double throw. And these switches are very common. You can find them almost everywhere. And there are 3 terminal switches. So from the circuit construction workshop, you have a switch that looks kind of like this, and you have a little knob at the top that goes from one side to the other. And when you build your circuit, you're building it so that when the switch is on, when the knob is on one side, those 2 are connected, and when the switch is on the other side, the other 2 are connected. The middle one is known as a pivot. So pin 2 in this case is known as a pivot. We are going to connect a screw to each of our inputs in order to provide the circuit more flexibility, provide it more utility, so it can be used more often. Whoop. So in this case, I'm going to go ahead and delete the wire and modify my circuit. So just click on the wire and press delete to delete the wire. And I'm going to move my switch into place. So I'm going to connect my screw terminal pin 1 into 2, and then the pin 1 from the switch into the 9-volt circuit. So if my switch is between positions 1 and 2, it will finish the circuit and current can flow all the way through to the rest. If my switch is flipped the other way and connected to 2 and 3, this is an open circuit. We're not going to put anything here. We're going to consider this as a open circuit. That means that the rest of the circuit will not be powered by the 9-volt battery. And this is important because in the event that we don't want to use the circuit anymore for any other application, we can just flick the switch to turn it off. Now there is a kind of like a deadly thing you gotta know about for switches, something called parasitic power. If the switch is flicked to the off position and it's left there for a long period of time and the switch is made really badly, sometimes there can be leakage current that goes from pin 3 to pin 1. It's something like when you have a kid's toy and you put like a 9-volt battery inside of it and you give it to the kid, they play with it once and they don't touch it for 3 months, they go after the toy and now it's out of battery, even though it was switched off, right? And that's known as parasitic power. So you have some amount of current going from pin 3 to pin 1. And that will exist pretty much no matter how great the circuit is made, but current will drain differently for better made screws compared to worse made ones. So we're going to go ahead and implement our switch into the rest of our circuit. Again, our pivot, which is 2, is going to be located at the screw terminal. So in this case, I'm going to go ahead and move this up. I'm going to drag the switch into place. And then I'm going to connect the wire from 1 to 2. Now, if the switch is connected between 1 and 2, it's going to connect with the rest of the circuit. Otherwise, it's going to be an open circuit and we don't care about it. Same deal with J3. We are going to go ahead and flip it so that 2, the pivot, is connected with 1 of J3. Then we're going to go ahead and connect pin 1 into the rest of the circuit. So if this switch is flicked on, then we can get 3.3 volts from the circuit. Otherwise, we won't. Same for 5 volts. All right. So in this scenario, we have implemented 3 switches into our circuit. And these three switches will allow us to turn on and off the power in both the 9 volts, 5 volts, and 3.3 volts terminals. Are there any questions so far? Is everyone on the same page? Yes, generally yes. Okay. So the switches are a feature, right? It's not part of the actual circuit, but we've added it there because it will allow us to turn our circuit off and on if we need it or if we don't, right? Let's say we don't need 5 volts, then we can turn that 5 volts off. The next thing we're going to implement is reverse polarity protection. Now, who can tell me what reverse polarity protection is for? What will happen? Yeah, bad stuff will happen if you hook the circuit up the wrong way. So in this case, 1 is 5 volts, 2 is ground. If we hook up the red wire of a battery to 2 and a black one to 1, you flipped it, right? And these components will start smoking. And you'll hear a small pop, and they'll be gone. It's really cool, just try something. Okay. Second thing that'll happen is your battery will get very hot. And that's not a good thing. You never want to put a reverse polarity through a 9-volt battery, because I think that somehow some batteries got really hot last time. We had about 2 batteries in the circuit construction workshop that got really, really hot. So be careful. And in order to prevent this from happening, what we do is we implement a reverse polarity protection diode. Now, who can tell me what the downfall of using a diode is in terms of reverse polarity protection? Not exactly power, but voltage, right? In this case, I'm not going to place a big diode. What I'm going to do is I'm going to put in 4001. Now this was power, hold on. A. 4001. Okay, the most 3 common diodes you want to use are 4001, 4004, 4007. They're cheap, you can find them everywhere, and they'll do the job. Not a quad NOR input diodes. So the 1N4001 kind of looks like this. You're going to go ahead and click this, and when you're using a diode, you always have to remember that it will have a 0.7 voltage drop across it. So if you're using something for like sensing the voltage in a circuit, you're not going to want to use this because you're going to lose some voltage. Same with if you are trying to detect some sort of if you're using it for like low voltage applications, right? Let's say you're designing an RF circuit that uses a reverse polarity protection diode. RF circuits run at about 3.3 volts. So if you put a diode there, you're essentially getting 3.3 minus 0.7 volts, which is like 2.7, right? 2.6. Yeah. So you want to be careful when using 4001 diodes. That's the moral of the story here. So we are going to attempt to connect a wire to this. I don't know why it's not letting me. And we are going to connect the entrance of the circuit through the diode into the rest of the circuit. So what this does is pretty much if the circuit is connected backwards and current starts flowing the other direction, current's going to try to go through each of these components and it's going to try to go through the diode backwards. When it does that, the diode is going to say no, because it doesn't have reverse polarity. It's going to stop the circuit from completing when you have reverse polarity. And that will save your circuit pretty much. The reason why we use the diode here is because we don't really care about whether it's 9 volts or not. We just care about 5 volts and 3.3 volts. So with a diode implemented, what will be the voltage, the approximate voltage at this part of the circuit? 8.3? Yes. So you'll find out with a multimeter that your input, if you measure it at the entrance of your AMS, will actually be about 8.3 and not 9 volts. And we can put 9 volts over here as an indicator. So again, remember that across a diode, you'll have a 0.7 voltage drop, always, unless you use like a super diode. And here it says, yes.
So if we use a diode but we actually wanted like actual 9 volts, you have to add more voltage?
Yeah, or you can use the PMOS model. So during the analysis workshop, we covered another version of the reverse polarity protection, which is called the PMOS model. You can go back and review it. Using the PMOS model, you'll get no voltage drop. So you just use a PMOS and a Zener diode and then a resistor, and then you can build it and have no voltage drop and protect yourself from connecting things backwards. Okay, but again, this diode is a feature. We didn't have to include it in the circuit, but we did because we wanted to make it better, right? We wanted to prevent our circuit from dying quicker, and we wanted to have more utility. We wanted end users, right? Whoever's going to use this in the end, which is probably you guys, right? To use the circuit for as long as possible and to use it for a lot of different projects and a lot of different applications. That's usually the reason why you design PCBs, by the way. You design them so you can use it later, and you can use a lot of them in different situations. So let's say you design a singular RC car driver circuit for one project. You can probably use it for another project as well, and save yourself the time of like wiring all the breadboard things together. Okay, the next feature we're going to add is an LED circuit. So an LED circuit consists of a power source, a ground, an LED, and a resistor. Can anyone tell me why we need a resistor in an LED circuit? To prevent from blowing out, correct, yes. Because if we don't have a resistor there, when the diode, well, the LED is a diode, so when the diode is in forward bias, it'll have basically infinite current running through it. And the diode doesn't like that, right? So it'll blow out. So you usually put a resistor there to prevent it from blowing out, and we are going to use an SMD resistor to do so. So as of the current moment, we are going to go back to our place menu, and we're going to search up resistor. So we are going to use R as a resistor. Okay. And remember, this is just a symbol, right? So it's not the actual circuit. So as long as you map the symbol to the footprint correctly later on, you'll be fine. So we have R, and then what we're going to do next is we're going to find the LED. So we type in LED, and it's going to be the first one. We rotate it into the right place, and what we're going to do is we're going to connect the 8.3 volts through this resistor and into the diode, and then into ground. So this right here is our completed circuit. Why is it highlighted like this? Oh, it's highlighting the net ground. Okay. Okay. All right. So this LED's purpose is to let us know clearly that this board is being used when the switch is flipped. When the switch is flipped, current is going to go through this diode and into this junction. Then it's going to split off into the LED circuit and also into the EMS on one side. Right? This is going to power the LED, telling us that, hey, this circuit is powered from 9 volts. And then the rest of the circuit is going to complete. Right? So I'm going to put this on every single one of these connections. So I have one LED circuit within the 9 volts. I'm going to have another one over here for 5 volts. I'm connecting that to ground. And then I'm going to have another one for 3.3 volts. And this will tell me if I'm using any of these voltages in the circuit. If you have more time, of course, you can go ahead and make this look a little bit prettier. But in this case, I'm just running through it. Okay, now where it's going to be important. We need to choose the right resistor values in order to prevent these LEDs from being too bright or too, not bright. It's too dark, I don't know. In this case, I'm going to use a 10K ohm resistor to power the first LED, because the first LED is powered using 8.3 volts. 10K is actually a lot for a resistor, but in this case, it'll limit the current going through the LED to around 20 milliamps. Actually, that's kind of high, 2 milliamps. Let's go with that. This LED, I'm going to say, is going to be a green LED. For the next one, I'm going to label this as a yellow LED. Now you can go ahead and label these with what you want this, I labeled the resistor, didn't I? This resistor I'm going to put as 3.3K. I'm going to label this as yellow LED. No, that's just the value field. So it doesn't really matter in the end, because you can put like the person assembling the PCB doesn't even have to follow that. They can put like a 10 million ohm resistor if they wanted to, right? If they wanted to. Yeah. So now we're going to go ahead and change this resistor value to about 1K. Because this is powered using 3.3 volts, and a 1 kilo ohm resistor will clamp the current down to approximately, math, is it 3.3 milliamps? Ohm's law. So you would take 3.3 volts divided by 1,000 ohms, which is about 3.3 milliamps. So 20 milliamps. Anything above that? Puff, pop. I'm going to make this a blue LED. And so, you know, I am in charge of a few different projects here at the school. And when I want people to assemble PCBs for me, I give them schematics that look like this. And so they can, you know, usually it looks neater. So not to feel too bad for them. But they can go and say, okay, there's supposed to be a resistor right here, which is R something, and that's a 10 kilo resistor. We're going to go ahead and put a 10 kilo resistor there. You can also label the PCB itself with the PCB silk screen with the name of the part, and that helps them out a lot too. The silk screen is the top layer of a PCB, by the way. Okay, now I have finished garbling up the names of these things. Let's see what we have. Our circuit, the core of our circuit, lies in these two AMS 417 chips. They regulate voltage from 9 volts to 5 volts to 3.3 volts, right? Then we went ahead and added our terminal blocks. We needed a way to plug in our dynamo battery and to get out our voltage in the circuit, right? That's our inputs and outputs of this black box. Then we went ahead and put our filters. We want to make sure that the current, the voltage going into these components is as smooth as possible. And the voltage we get out from the circuit as smooth as possible, right? No earthquake-like voltages here. Next, we went ahead and add switches because, again, we want to use this circuit for a long period of time, whether to power Arduinos or microcontrollers or RF. And if we want to use it for other applications, we want a way to turn it off. So we added switches here. Then we added reverse polarity protection because we want to make sure that if we gave this to our friend and our friend wanted to break it and flip it backwards, it wouldn't blow up, right? So reverse polarity protection. And then we added these LEDs. These LEDs are indicators to indicate whether the device has been turned on or not. It's always really nice to have these because it's always really nice to know that your circuit is at least running, right? It eliminates one thing off your troubleshooting list if this thing breaks. Yes? Good question. Okay, the question is, does this yellow LED, the junction here, have to run below the switch? And it depends on what you want. And in this case, it depends as well. So let's break this down here. When I connect the end of the line to before the switch, right? When will this LED turn on? In what condition? This yellow LED would only turn on if this switch was connected to the circuit, right? If the switch is not connected, this yellow LED would turn off. This indicates to us that this 3.3 volt voltage is not connected with this 5 volt is not connected with the rest of the circuit. We're not getting voltage. We're not using it, right? This is actually the correct application because we don't want this yellow LED to be turned on all the time. That's a waste of energy. We only want LEDs to be turned on when we're actually using it, right? So great catch. This wire actually has to be before the switch as well. Otherwise, the blue LED would be turned on all the time. Now you might be asking, hey, wait a minute. This green LED is after the switch. Can anyone tell me why that is? Right, it's the input power source. So this green LED will not turn on unless we flip the switch and connect dynamos to the circuit. This is kind of like our main indicator that the circuit's working, right? We need to make sure that the green LED is turned on. All right. So there you have it, a circuit, a functioning circuit. Now you can improve this circuit and make this schematic look neater by using net labels. Anyone familiar with what net labels are? They're really cool. All right, I'm going to show you an example of a net label really quick. But we're not going to implement it for the entire circuit. The thing I love most about PCB design is how neat you can make circuits. And one of the ways you can do that is by isolating different parts of the circuit from each other. So for example, If I went ahead and cut off the switch from the rest of the circuit, right? And I just did something like this. Wire. Okay. So in circuitry, a net is a connected string of wire. If I had a bunch of wire going all over the place, we would call that a specific net. The ground net is wherever the ground wire is connected to a component. So this would be part of the ground net, this would be part of the ground net, and everywhere else that has a ground will be part of the ground net. When you get to routing the PCB, you want to connect all these nets together in order to make this complete circuit. Now, this wire and this wire are supposed to be connected together, right? But they aren't. The reason they aren't connected yet is because they don't have a net to each other. These two are separate nets as of right now, but we know that we need to connect these two wires together. Now, I'm going to show you a very extra way of doing so, using portals. So you can think of portals in this case as sort of an invisible way of connecting those two wires together using a net label. So on the side here, if you go ahead and put in a net label like this, and I say, for this one, it would be 5-volt sample. Let's say that. You can place the net label on top of a wire, copy it, and place it on the bottom wire. Now, because these are the net label, the system now knows that these two wires should be connected together, right? So now if you have a mess of a wire, like a circuit system, you go ahead and say, okay, I can separate parts of the circuit, drag this part all the way up, and say, okay, that's an LED circuit. The rest of the circuit is down here, but parts of it are fragmented. So it's a better way of organizing your circuit. If you have a lot of different parts combined together, you can split it off, put a net label to connect something very far to the main circuit. Does that make sense? Any questions on this? Portals? Yeah?
So is it just for neatness and you couldn't just extend the wire?
You can extend the wire, but it's just for neatness. Yes. Because sometimes, like, if you give me a schematic that's filled with wires, I'll hate you for it. I don't want to like trace wires from like one location to another. That's like really, that's like not my forte. I want to look at the schematic for 3 seconds and know what I'm doing. Yeah. Yeah. In fact, I'm gonna prove a point. 3x is 2. Okay. Let's show an example. Okay. Can't really see it very clearly here. But for example, you have an Arduino, right? And Arduino has a lot of pins. In this case, all of the Arduino pins are used. It'd be a hot mess if you connected the wires from the Arduino to the rest of the circuit, right? Instead of doing that, I have each circuit separated off into different components. For example, this would be a regulator, right? This is a solenoid actuator circuit, but it's connected to the rest of the circuit by like sol 1 and sol 2. This goes to the Arduino, by the way. So some pin of the Arduino, instead of having a wire snaking down all the way over here, I just put a portal. Connect those 2 points together. Same with this part. This is a voltage detector. I just put A0, A1, A2, A3 here, so that I can map it to A0, A1, A2, A3 up here. Again, if I had wires instead of net labels, I'm just going to have a mess of wires coming down into the center. And then you're going to have overlapping wires, you're going to have junction wires. It's going to look very disgusting. Right? Then I have like an L298 motor driver, and also a step-down circuit. Like this is just a very nice way of presenting, where everything goes in the circuit. Because there's a lot of different intermeshing networking parts when you're doing something as complex as trying to drive a car. This is for an RC car, by the way. Like this? Cool. I have a lot of other examples if you want to see it. Okay. So when we build the circuit, we'll go ahead and see that the 5-volt sample will transfer over, and it'll prompt us to connect those 2 nets together. All right. But for now, we have completed the schematic. The next step is we're going to make the PCB. Making the PCB is very fun. A PCB has a couple layers that you got to note. There is a silk screen layer, which is where the top of the PCB, the first layer of the PCB lies, and then there's a top layer for copper, a bottom layer for copper, and then a bottom silk screw. Those 4 layers are pretty much the only 4 layers you need to know for now, right? And this is called a 2-layer PCB, right? Because there's only a top layer for wire, and there's a bottom layer for wire. So we're gonna go ahead and head back to the other screen of our KiCAD. Actually, not yet. First, we're gonna go ahead and go to, remember this. It is this button up here, maybe. No, just kidding. Run footprint assignment tool. Okay. Before you build the PCB, you need to let KiCAD know exactly what each of the items are, right? Because it doesn't know what this diode is, it doesn't know what this capacitor is, at least it doesn't know what the model is in the PCB driving software. So what you need to do is to assign it to one. And luckily, KiCAD already has a lot of them. So we're gonna go ahead and click this button. Oh. Okay, by the way, this is the automatic annotation. I'm just gonna go ahead and click annotate real quick and automatically do it. Okay, so that automatically annotated every single one of my components with the J1, J2, SW1, those components. And in case you don't like how it's laid out, you go ahead and change it later. Okay, but for now, if you go ahead and press assign footprints, now this is very important. You need to give each component its model, its 3D model. So what you're gonna do is I'm gonna go ahead and, because I know I want SMD components on this, I'm gonna type in 1206 in my top bar here. And I'm gonna go ahead and select capacitor SMD. Everything on the left here are what's called footprint libraries. They contain a lot of the footprints, which are the models for the PCB, and it has all the correct pads and the correct spacings for you to solder something on. So in this case, I will choose a capacitor SMD and a 1206 capacitor for all of my capacitors. Now you'll notice that I'm going to choose the same footprint for each of them. Because again, it doesn't matter what it is, right? You just add on capacitors later on. You're not, specifying that every capacitor is the same in our footprint or a schematic. Later on, if you order like mass PCBs that are already soldered for you, that's called SMT or SMD assembly for like JLC PCB. You'll have to create a bill of materials that correctly lists all the different types of capacitors you want, because the fabrication company is going to make the PCB for you, and you don't want them to like put a 10 microfarad capacitor when you actually want a 1 microfarad capacitor. So in that case, you want to be specific then. But right now, no. For the LED footprint, I'm also going to use an 1206 footprint, but here this time I'm going to put an LED. So if you scroll down, you'll see a box here called LED_SMD. We're going to use the same size 1206 for a SMD footprint. We click on here, we see we have LED 1206 metric. We're going to go ahead and click that. And then we are going to assign each of the LEDs to the 1206 footprint. By the way, if you guys didn't know, 1206 is the very biggest SMD component you can find, right? You can solder this, and I love this comment by Stack Overflow. You can solder this with your hands behind your back, blindfolded, and not being able to see anything, because this is so large. If you get to different SMD sizes, like 10603, 0420, something smaller than that, it's going to be really hard to solder with a soldering iron. You're going to have to use something like a heat pad and a hot air gun in order to melt solder beads onto it. That's a whole different story. You'll get to do SMD soldering, hopefully, maybe this semester or next semester in one of our workshops. But in this case, 1206 capacitors, 1206 size, that's just size, can be soldered really easily. That's the point I'm trying to make. Okay, next is the screw terminals. For screw terminals, we're going to go to connectors. And then I believe it's connectors, TE connectivity. I don't remember what part it is. Let's see. Might not be this. I don't remember. I don't remember which one it was. Maybe connector. It was not that. All right, hold on. All right, so we found it. Yeah, the recording will never know. Okay, so go ahead and scroll down to terminal block, and then search up Bornier. Bornier, yes. And the component is called terminal block underscore Bornier-2. Now this is going to be 5.08, which is the space between the pins. So you're going to have your blue terminal block. You'll notice when you put it on the breadboard that it spans two little pin thingies instead of one, and that's what it's for. So we're going to go ahead and select this. Press OK. Just kidding. Don't press OK, because I wasn't done. Come back. Come back. Okay. All right, now I have to like go back down to it. Terminal block, Bornier, sign. Okay, good. All right. So now that we fixed our terminal block assignment issue, now we can move on to resistors. I'm going to go ahead and use SMD components for resistors again. Now, the only reason why I do this instead of using through-hole components is because the SMD components make the footprint smaller. Generally, in PCB design, you want to make your PCB as small as possible because A, it's cheaper. It's cheaper. No, that's pretty much the only reason. Like, if you like need a bigger PCB, you can like design for one. But usually, if you want to make it in like good quality fabrication companies like Osh Park, and I think DigiKey is a new one, like it's like DigiKey Red. Those will get you the PCB as fast as possible, but like it costs a lot of money. It's like $10 per square inch or something like that. While like JLC PCB, for every single PCB under like, it's like this big, you get like PCB this big, you get like 5 of them for like $1. Literally how cheap it is. But the shipping costs are expensive and you'll like get it to you in like 2 weeks because it's from China. So you pick and choose, but in general, SMD components make your PCB a lot smaller and it costs a lot less. So for resistors, I'm gonna go ahead and scroll up to resistor SMD. I'm gonna search at 1206, and then I'm gonna choose my 1206 metric for my resistors. Okay, now we're on to the switch. Now here's the problem. The KiCAD doesn't have, a footprint for a switch because it's just not a thing. And don't worry, I've searched on it. It's proof on my screen. You can find it out. But like, we're gonna have to make our own footprints for this. And so, cue the unnecessary Amazon image of a switch. This is what we're making. So we want to make a kind of footprint. Yes, Mark?
So footprint and the dimensions of the switch?
A footprint is what you're putting on the PCB itself. So it's like your model on the PCB. A symbol is what's on the schematic. So in just general PCB terms, you have 3 main different types of forms that all represent the same component. You have the symbol, which is on the schematic. You have your footprint, which is on the PCB, and you have a 3D model. In case you want to like put a 3D model on there, it's not required though. So we're concerned about footprints here. How the PCB designer software is going to know that on the PCB it is going to be something that you can put the switch on, right? This switch says it's going to be about 0.8 millimeters thick, 4.7 between each of the legs of the switch, and there's going to be 3 of them. So when we make a PCB, we have to, or with a PCB footprint, we have to design it in such a way that it'll allow this switch to fit inside the PCB board. So what we're going to do here is we don't have a footprint for this, so we're going to make one. We're going to press OK, and we are going to go back to our main screen, and we're going to click on Footprint Editor. So again, a footprint is kind of the, like there are the holes or the pads that lie on the PCB for you to solder things onto. So it's on the PCB itself and not in the schematic. So we're getting physical here. What we're going to do is we're going to go to Preferences, and then we're going to go and Manage Footprint Libraries. Now, when you manage footprint libraries, you can see all the different libraries in which we just searched through for these components' footprints. We're going to make a new library, and we are going to call it Custom Parts. So we're going to go ahead and click a new one here. We're going to name it Custom Components with an underscore in the middle. And this underscore is really important because if you have just a space instead of an underscore, your entire file system will just crash down and burn. So we're going to go ahead and create a new folder. I'm going to create this folder inside my KiCAD folder. And I'm going to go ahead and name this folder Custom Components. Okay, we'll select the folder. And then in the description, I'm just going to put Custom Components. I'm going to press OK. Now we have to speed things up here because we're not going to finish on time. What we're going to do is we're going to place 3 pads. Now that we have our custom components, we're going to go ahead and match footprint libraries. If we scroll down, we can see that we have a new folder here, so that's good. Okay. I'm going to go ahead and create a new empty footprint, and I'm going to call this my slide switch. My footprint type is going to be a through hole, and I'm going to press OK. This through hole is important because it has to go through the PCB, right? There are 3 legs on that switch that go through the PCB. What I'm going to do here is I'm going to place a pad. A pad is kind of like a hole in the PCB surrounded by grounding material. In this case, I'm going to change the dimensions on my hole to the rest of the switch. So in this case, my hole will have a, hold on, this is a reference then. Pad, yes. Oh, come on. Okay, I'm gonna drag this out of here first. Okay, I'm gonna double click on the pad, and then I can change the pad's hole size, I can change its circular structure, and other things like that. So I'm gonna go back to my dimension, and I can see that it is about 0.8 millimeters thick. I'm gonna make it 1 millimeter just for tolerance reasons, right? You always want to assume that they're gonna mess up on the size and make it smaller than it's supposed to be. So I'm gonna go ahead and make the hole 1 millimeter, and the pad size 1.2 millimeters, 2.5 millimeters. Actually, I'm gonna make it a little more. 1.5 millimeters for the pad size. Okay, so now that we have our pad size, we're gonna press OK, and it has been enlarged, which means that the leg of the slide switch is gonna go straight through the hole. Next, I'm gonna click on the pad, I'm gonna press Control-C, and I'm gonna copy it. Now I want to place this hole 5 millimeters away from the first hole. So what I'm gonna do is I'm gonna change my grid to 5 millimeters, and then I'm going to go ahead and just go 1 space out. So it's gonna snap in place, right? Now I'm gonna copy this, whoops, and then place one on the left. So now I have a switch with 3 distinct holes for me to place the switch into. And in addition, it has been properly spaced and dimensioned according to the dimensions of the switch. Now, in case you don't trust this dimension, you can use a set of calipers and do it yourself at home. But this is just a general one. It looks pretty good. Even though it says 4.7, it's actually 5. So in this case, I'm going to go ahead and just say yes. I'm going to use this as my dimension. Oh, actually, okay. Now you gotta be careful. This is a drawing and shows the side drawing as this switch being 1.3. So it's actually 1.3 millimeters on the side now, and we set it as a 1 millimeter hole, which means if you produce this PCB, the switch is not gonna fit. So you gotta be careful. So this is 0.8 because it's on the side, but if you turn the switch on the side, you'll see that it's thicker. So we need to enlarge the hole so it's 1.5 millimeters in diameter and not 1 millimeter. So again, you can always check by looking at your calipers. So 1.5 millimeters and 2 millimeters for pad size. The pad size, you don't really have to like, do an exact measurement. You can just like wing it, but just don't get too excessive. Okay, so now I'm gonna go ahead and copy these 2 holes and place them on either side. I'm gonna change the pad number of the center one to 2, and the pad number on the left hole to 3. Now, why am I doing this? The reason I'm doing this is because the center one is my pivot. So if we look at the schematic, 2 is going to be the center, right? And then 1 and 3 are going to be on either side. Now, if 2 and 3 are connected, which is my convention, if 2 and 3 are connected, the switch is going to be off. And if I slide the switch to the other side, 1 and 2 are going to be connected, which means on. Right? So we've created a footprint for the switch, which means that we can now import it into our circuit and use it to our advantage. Last thing I'm going to do is I'm going to go ahead and create a rectangle around this, a little bounding box, if you will, just so that when it shows up on the schematic, we know that it's a switch. Oops. Okay, I'm going to make the box a little bit smaller. so it goes ahead and doesn't take up too much space, because remember, space is money, quite literally money. Yeah,
How does circuit have like square ones?
you have square pads.
Yeah, I don't know.
Okay, you created an SMD component. So go ahead and create a new footprint, but this time make sure you select it as a THT. So Mancha had a red pad, which means that it's something to be soldered on top of PCB, right? A circle means through hole. A pad means SMD. So a pad doesn't let you, put items through, and it's usually smaller in size. Okay, so I'm going to go ahead and save this footprint, and I'm going to save it as slide switch. I'm going to scroll all the way down. Oh, just kidding, not all the way down, to my custom components library. I'm going to save. Okay, now that I've saved this as a custom footprint, I'm going to go back to my schematic. I'm going to click on Run Footprint Assignment Tool. And then I'm going to press on my SPDT switch. And where's my custom components? Custom components, here we go. I'm going to use my slide switch footprint that I just created. I'm going to apply, press OK, and then I'll be done. The next thing to do is you want to go ahead and go to Tools and Update PCB Schematic. This will take all the components on your schematic and then put it onto a PCB for you to view. I'm going to press Update PCB. There should be no errors. Press Close, and then just plop everything down onto the surface. So you'll see this is a gigantic mess of, like switches, capacitors, diodes, terminal blocks, EMS, basically everything you need to place on a PCB. The next step is actually just to move these around into place, right? To make that PCB you saw inside the PowerPoint. Okay, now at this point it just looks like a bunch of garbage because there's no wiring, there is no specifications for anything. It's just a bunch of components. But even in this state, we can see what it looks like, or see what the PCB is starting to look like. If you press Alt-3 on your keyboard, a window will pop up showing you exactly what this PCB is supposed to look like. Right? You can see there's a bunch of components on it. These are the 3D models for each of the capacitors, the diodes, the resistors. Here's the AMS117 for the voltage regulator, and the diode 3 model. Notice that there's no 3D model for either the switch or the terminal block connector. If you want to add a 3D model there, you can, but I'm just not going to. What we're going to do next is organize this to make this look nicer. So I'm going to start by taking the AMS117s and then putting them next to each other, right? You always want to start organizing everything by using the core components. In this case, it would be the AMS117s. Next, what you want to do is I'm going to go ahead and place our terminal block connectors, right? Because the terminal block connectors was what we did next on the schematic. So we have J1, J2, and J3. I'm going to rotate them so that they are in the same orientation as we have designed it. So in this case, I would rotate it like this. And you can see the labels on here. We have a net label and we have earth, right? So we'll do the same thing for the top and the side. And I'm going to go, whoa. I'm going to go ahead and rotate it. So that earth is on the bottom. Now there is no convention that tells you whether like a VCC is a square hole or ground is a square hole. It's up to you to use that as a convention. So next we're going to go ahead and implement the capacitors because that's what we did next. We used the filtering capacitors on the AMS117, so like one right here. There's C2 that goes on AMS117. Then C3 will go in between. We're going to find C3 here and drag it. C4, C5, and C6. Okay, Now that we have these capacitors dragged onto the board, the next thing we're going to do is we are going to implement our switches. Now you can start to see how this PCB is starting to look like something like our schematic here, right? We'll drag this a little bit to the left. We're going to put our switch 1 in between the terminal block and the AMS 117. Our switch 2 in between J2 and the rest of the circuit. And switch 3 in between this terminal block and the rest of the circuit as well. We're going to put the diode, because the diode, remember, is for reverse polarity protection, very close to where it's actually supposed to be in the circuit. It's not going to be exactly correct, but it's going to be close. I'm going to flip it so that it's easier to connect with the circuit. You'll note that we have some lines here, and these lines indicate that they're supposed to be actual wire connections. They're supposed to be connected to each other so that they make an electrical connection, and it will do what our circuit is supposed to do. So in this case, the diode is supposed to be connected from the 1 pin into the AMS. Right? So our next task is to connect the LEDs, which is actually the last part of our circuit. So we'll have our R1, and I think it's D3. This is our green LED. And then we have our D2 and R2, which is in the middle. And then our R3 and D4, which is at the very end. Now, of course, if you want to go ahead and make this placement more precise, you'll go ahead and change the grid size to something lower. It would be like this, right? This will allow you to get more precision, but still keep still retain the snapping motion of your PCB design. So something along the lines of this, right? Okay, let's press all 3 again once you've got all the components placed on your PCB. And you can see that it's more or less, in the correct orientation now. We're getting closer and closer to what the PCB should look like. All the components are on there, and all the holes are neatly placed as well. What we're going to do next is called routing. Now, routing is a bit tricky because you have to take into account like how much current is traveling through your board and what voltage rating your board is at, and things like that as well. Now, for IPC standards, 1 amp of current is going to run through this PCB. And I know that because this AMS can only take 1 current. Anything above that is going to blow. So 1 amp of current equates to around 15 mils of trace. Actually, it's around 10 mils. 10 mils is just, or a mil is a thousandth of an inch. And 10 mil is like the trace width. 1 amp equates to 10 mils, but we're going to go to 15 mils because we want to make sure we don't get any current spikes, any random current spikes. If you don't design your PCB so that your trace width is equivalent with IPC standards, if you use a smaller trace width for a very high current, your PCB is going to catch on fire. So that's why you got to be very careful with PCB sizes. Okay, so the net class width is pretty much the default width. And if we edit the predefined sizes, we're going to go ahead and add something like 15 mil, like that, and we're going to press OK. Now for the track, we're going to change this to 15 mil, like this, which is 0.381. And the next part is very fun. So what we're going to do next is we're going to press this wire button on the side here. And we are actually going to start connecting the lines. So this process is called routing. We are creating the wires that we place in the schematic. So for example, if this is supposed to connect to, if the terminal connector is supposed to connect to the switch, you'll see a line. That is called a net. A net is just a wire that connects from one point to another, remember? So we're going to go ahead and connect these 2 points together using a wire. For example, like that. Now this wire is consistent of a bit of copper that gets poured onto the top layer of your PCB that forms an electrical connection between your terminal block and your switch. So now what you're going to do is you're going to go ahead and repeat this for the rest of the connections. So for example, you'll see here that this connection actually goes very far, right? The end of D1 goes to net C1 pad 1. Let's see what that is. hold on. This doesn't look right. Isn't that C1 pad 1? Right, okay. So the end of this diode, when you click on it, it's supposed to go to the following connections. And I realize now that I've switched the AMS chips because that didn't look right. So you gotta be very careful about labeling your things correctly in this case. Okay, I'm gonna switch these. And then drag the U1, U2 chips in the right place. And now, the end of my diode, I can connect it to my AMS chip, like here. And then I'll just go ahead and connect the rest of the dots, like so. And you'll notice that I'm not connecting all my earth pins. The reason I'm not doing that is because I'm going to do what's called a polygon pour later on. And the polygon pour is pretty much going to connect all the earth pins together, which is why I'm not doing so first. It's a little bit of a shortcut that I like to employ to make my life a little bit easier. That way you don't have to connect like 8 billion different pins. Now this is a good time to talk about auto routing. Altium has a feature called auto route, or auto route, however you say it, that does this automatically for you. Now that is okay, that you can use auto route if you want to, but a lot of times if you have a more complex circuit that requires routing on both sides of the board, because you don't just have to like do routing on one side, you can do it on the other side as well. Altium doesn't know like how much current should travel through a specific part of the board, because sometimes you might have 1 amp going through one part of the board, but then like half a milliamp going through another part, very low current. So Altium can't tell the difference. You need to manually route things, even if you use an auto router, because otherwise you'll run it into like you might make a mistake. And you don't want to make a mistake when PCB designing because it takes so much time to fix. And money, so much time and money. Can't forget about the money part, right? So I'm gonna go ahead and continue with connecting the rest of these connections. Okay, you'll see here that this connection for the LED, I have to go around it. Another rule of PCB design is you want to make sure, or you want to try to have the shortest connections possible between 2 points. So if I flip it, then I'm able to connect these 2 points together successfully, right? And notice how I'm still not connecting any earth pins together. So I am speedrunning this like a ton, a crap ton. But when you're doing this on your own time, this takes a while. This takes a really long time. When I did this the first time, when preparing for this lecture, I literally spent about 3 streams doing it, which was like 3 hours, 4 hours. And that's with me knowing what I'm doing. A lot of times before you send this out to production, you have to stare at your PCB design for a long time just to make sure you didn't make any mistakes and to make sure that everything is in place as you want it. In this case, I'm going to just assume that I connected everything and I'm going to start making my board outline. So if I press Control 3 to take a look at the 3D view, you can see in the 3D view that all the routing is complete, but it still looks like this rectangular shape and it kind of looks very ugly. When I make a PCB, I want to make sure that I have rounded edges and mounting holes. And this is kind of like a quirk of PCB design. You can do things like that. I'm going to go ahead and click on my, let's see, edge cuts. I'm going to go to the edge cuts layer on the right-hand side to place my board outline. I'm going to draw a line. I'm going to increase my trace width, and I'm going to draw a track on copper layers only. Whoops. So I'm going to choose a line. I'm going to draw a line that goes all the way around my PCB. Something like this. Okay. Now, since this line is on the edge cuts layer, what's going to happen is the program is going to automatically assume that this is the edge of a board. So if I press Control 3, well, that was already there. It already did it for me. But if I do something cool like make an arc, right? And I reduce the, and I reduce the lines on the side, Oh, come on. Okay. So I have a bent edge like this, and I press all three. Uh-oh. It didn't process that, fortunately. Board outline is missing or malformed. Oof. Oh, I did. Thank you. I didn't even see that. Okay. There you go. Okay, so you need to have a closed shape in order to make a board outline. And you can see there now you have a bent edge. So I like making these bent edges because PCBs are sharp. You can like throw them as like a shuriken and kill someone with it. So don't do that. Make round edges, make them nice to hold. And you can like give them away like business cards too. Dang, I wish I had brought some PCBs here for today. It'd been really cool to show it to you guys. Okay, so I'm just gonna do this for the rest. And then I'm gonna make a round edge for here. Oops. Here. And then I'll have to resize each of the lines. Now, like I previously said, this process takes time. And so you need a good amount of patience in order to endure the struggles of PCB design. But it's a lot of fun. The end product is worth it. Okay. So now that I've made, kind of looks off-centered. I think I made like one of the curves a little bit too thick or something, but it's okay. Now we have, yeah, that top right corner doesn't look right. Screw it. So something you can do is you can make mounting holes. So if you make a circle on KiCAD, and by the way, it's really easy on KiCAD to do this. It's a really pain in the butt to do it on like any other program like Altium. You can go ahead and make a tiny hole, something like this, for a screw. So if you're putting this onto like another design, maybe like you're putting this PCB on a car, or you're putting this PCB on like a Hyperloop pod, right? You would want to have mounting holes for it so that you can drill it onto whatever you have, and it'll hold it in place. So I do all three. Now you can see that I have a hole here. A popular question for mounting holes, this time, it's 801. Popular question for mounting holes is it grounded? And in this case, no. Sometimes you want ground screws, sometimes you don't want ground screws. It's your personal choice. Personally, I don't want to. Grounding screws just means putting a pad where that hole is and putting it to the rest of the net. So in this case, I'm not going to do that, but if you want to, you can. It doesn't hurt the circuit. Okay, last thing I want to cover before we end for today is what's called a polygon pore. So I believe it's inside of here. A polygon pore is a mass of copper that spans over a large area of your PCB. So for example, if I want all my ground nets connected together, I would have to put a polygon pore that covers the entire PCB and then set it to the earth node. And it does something really cool. It saves you from connecting a lot of things. Because the routing process isn't usually this simple. Usually it's a lot of headaches and trying to make sure that no lines cross each other, because like you can't cross lines. It's not like a traffic jam. Like if I want something to cross this line, I have to put it either on another layer or use a via. So in this case, it's kind of like a puzzle. It's kind of like Tetris, like Vicky said. But in this case, I'm going to go ahead and draw a polygon. In this case, I think it's actually add filled zone. It's on the side here. So you go ahead and do add filled zone, and you draw a little rectangle, net non-copper zone properties. I have to put it on the front layer because you've got to remember to change your layer before you do this stuff. Okay, so you'll get a window that looks like this, and you want to go ahead and select Earth. So I'm going to select Earth. I'm going to press OK, and now I'm going to draw a rectangle around my entire PCB. So once I draw that entire rectangle around PCB, you can just see exactly how off I was on that arc there, but you know, it's in the past. I'm going to go ahead and press the letter B. Now B will do something what's called a repour. When I press B, it'll go ahead and pour the copper onto my PCB, and it'll also connect my earth together. It'll put a line through all the earths of the circuit, here, basically connecting them all together. And this is great because it's saving me a lot of work and not having to do the earth connections manually. All right. Now if we press Alt 3, you can see that our board is actually pretty much complete. Now, you can spend like a couple hours organizing everything, labeling everything so it doesn't just look like SPDT1, putting everything back in place. But just in general, this will do what it functions. You can order this on JLC PCB or something similar and get it fabricated for you, and you can solder all the switches and all the terminal blocks on it and all the AMSs and all the SMD components. And then you can use it as a voltage regulator, yes.
So with the core, you only need to ground once and not everything.
Yes, because it's all over the place. It pours copper literally from the entire PCB, and then it just connects all the ground together in the process. So this is something advanced, but if you want some sort of smooth signal through your circuit, a popular technique is putting a polygon port of 5 volts on one side and then ground on the other. This makes a big smooth capacitor, basically. And so I'm not going to do that here, but if you want to do it in the future, you can. It makes your PCB work better, basically, if you have any high frequency signals. High frequency being like 1 gigahertz or above. Okay, so that was the last topic I wanted to cover. Again, you can go ahead and do more fancy things such as making your lent labels. Vicky removed the picture I had of my circuit. I'm just going to display it real quick. So this is the final circuit. It took me like 4 or 5 hours to actually place everything and label everything on there. But in general, that is the process of making a voltage regulator PCB with maximum utility. So we can do this, we can have switches, we can have things to plug in, things to take out. We have diodes in order to tell us where things are. We have reverse polarity protection. We have filters. Is there anything else? So it's a lot of utility packed into one PCB. And you can go ahead and order this on any fabrication company and get it physically made. In fact, because you guys are here today, we are going to order a bunch of these PCBs and provide them to you during some future workshop for you to put together. So you'll get the opportunity to actually see this in real life and solder it together as well. Now, in addition to that, if you would like to design your own PCB and you would like to order it and see what it looks like in person, you can go ahead and do this over the weekend. I think our deadline is this or next Sunday, probably next Sunday. If you turn in your PCB Gerber file into one of the instructors or one of the leads for Hyperloop, we'll order it for you for free. And you'll get your own design, you'll get to solder parts into it, and you'll get to avoid that nasty shipping fee that everyone dreads. By the way, it's like $80 for like 100 boards, so it's like insane. So I think that's all I want to cover. Actually, one last thing. How do you actually generate a Gerber file? So you'll go to File, you'll go to Fabrication Outputs, you'll select Gerbers, and you'll get this menu. Now, in order to fill this out menu, you're converting your PCB into a format that the fabrication company can understand in order to manufacture your components and manufacture your board. There is a very specific, guide, my voice is dying out, that you must follow that you can Google online. So you can just type in JLC PCB, KiCAD, Gerber file, and each fabrication company has different instructions for you to follow. You're going to go to how to generate Gerber and drill files in KiCAD 6, and then you're going to go ahead and follow these instructions here. And then after you've done this, you take all your files, you zip it up into a zip folder, and then you give it to the company or one of us for us to make. All right, so that is all, actually. I know it was an information overload, but are there any questions? Yes.
Yeah, so what are so you're talking about designing your own PCB. What are the constraints on that to get it?
So I think the only constraint would be it has to be less than 100 millimeters by 100 millimeters in size. So don't go crazy. Don't make another one. So as long as it's under that size constraint, you can make a couple copies for you. And you have to get the design into us by next Sunday.
Well, you make it through advance.
Yes. That's why it's like good for bulk order, because shipping costs and stuff. All right, I'm gonna end the recording here for the people who are watching on Zoom, but thank you so much for watching. If you have any questions, you can always feel free to let one of us know. I know this was a bit of a rush job. Will be a longer version I'll post with probably more commentary, more entertainment for my Twitch channel, so you can go look at that as well. But other than that, thank you so much for watching this video, and I hope you learned a lot, and I hope you have a great rest of your night, all right? So good night.